Recursively defined sequences. Definition. A sequence a sub 1, a sub 2, a sub 3, and so on of real numbers is said to be recursively defined if 1. For some fixed number t, the terms a sub 1, a sub 2, and so on up to a sub t, that fixed number, are given. 2. For each integer n greater than t, a sub n is defined in terms of one or more of the values a sub 1, a sub 2, and so on up to a n minus 1. Here in part 1, the a sub 1, a sub 2, and so on up to a sub t are called the initial values of a sub n, and frequently there is only one of those, and we'll look at some examples where there's one or two initial values, but t could actually be any number. While the relation that defines a sub n in terms of a sub 1, a sub 2, all the way to a sub n minus 1 for n greater than 1 is called the recurrence relation for a sub n. That's what we see in part 2. So each definition has two parts, some fixed number of initial terms, and then the recurrence relation that defines the rest of the infinite number of terms of the sequence. For example, the Fibonacci sequence f sub 1, f sub 2, f sub 3, and so on is defined recursively by f sub n is equal to either 1 if n equals 1 or 2, or f sub n minus 2 plus f sub n minus 1 if n greater than or equal to 3. The top line, the 1 if n equals 1 or 2, defines the initial values, and below that is the recurrence relation that uses the values of f that come just before f sub n. So, using the initial values in the top line of the definition of the sequence, we have f sub 1 equals 1 and f sub 2 equals 1. You see that n is 1 and n is 2, we get 1. And f sub 3, we would have to use the recurrence part of the relation. F sub 3 equals f sub 3 minus 2 plus f sub 3 minus 1, substituting 3 for n, which is equivalent to f sub 1 plus f sub 2, which are unknown values of the sequence. Each is 1, so we get 1 plus 1 equals 2. You see, this definition and how it works is very much like the piecewise functions that you studied in college algebra. Each part of the piecewise function is defined differently depending on what elements of the domain are used for that part of the definition. In our case, the first part is defined for n equals 1 or 2, and the second part is defined for n greater than or equal to 3. So, unlike the previous explicitly defined sequences, we can't immediately find any a sub n, like a sub 5, because f sub 5 depends on f sub 4 and f sub 3, the two in the sequence right before it. So, let's look at some other elements of this set. F sub 4 equals f sub 4 minus 2 plus f sub 4 minus 1, replacing n by 4, and then doing the subtraction. That means our subscripts are 2 and 3, so we have f sub 2 plus f sub 3, and we know f sub 2 is 1 and f sub 3 is 2, so 1 plus 2 is 3. F sub 5 will be, substituting 5 for n, f sub 5 minus 2 plus f sub 5 minus 1, And so our subscripts are 3 and 4, the two that are right before 5. So we have f sub 3 plus f sub 4, and f sub 3 is 2, f sub 4 is 3, so 2 plus 3 is 5. One more. F sub 6 is f sub 6 minus 2 plus f sub 6 minus 1 equals f sub 4 plus f sub 5, the two members of the sequence right before f sub 6. So we have 3 plus 5 equals 8. Or our Fibonacci sequence is looking like this. 1, 1, 2, 3, 5, 8, 13, 21, and so on. And you see 21 is the sum of the two before it, 8 and 13. 13 is the sum of the two before it, 5 and 8. 5 is the sum of the two before it, 2 and 3, and so on. Here is another recursively defined sequence. The sequence a sub n for n elements of the natural numbers is defined by a sub n equals 2 for n equals 1, and a sub n equals 2 times a sub n minus 1 plus n for n greater than 1. So this time we have only one initial value. A sub 1 is 2. And then all other elements of the sequence are defined recursively using a recurrence relation based on the term before them, because a sub n minus 1 comes right before a sub n. So a sub 2 would be 2 times a sub 2 minus 1 plus 2. Notice there are two n's that we have to substitute into. One is in a subscript, and one is part of the arithmetic. So we have 2 times a sub 1 plus 2, or 2 times 2 plus 2 is 4 plus 2, or 6. A sub 3. We have to substitute 3 into two places in the definition. The first is in a subscript, the second is a term that's being added. So we have 2 times a sub 3 minus 1 plus 3 equals 2 times a sub 2 plus 3 equals 2 times 6, because we've already found a sub 2 to be 6, plus 3 is 12, plus 3 is 15. A sub 4 is 2 times a sub 4 minus 1 plus 4, substituting 4 for both ends, which gives us 2 times a sub 3 plus 4, or 2 times 15 plus 4 is 30 plus 4 is 34. A sub 5 equals 2 times a sub 5 minus 1 plus 5 equals 2 times a sub 4 plus 5, and a sub 4 we just found to be 34. So we have 2 times 34, which is 68, plus 5 is 73, giving us the sequence 2, 6, 15, 34, 73, and so on. The important thing to remember is in recursively defined, if, for example, we needed to find a sub 10, we would first have to find, using the definition, all of the terms before 10, a sub 1 through a sub 9, and then we could find a sub 10. In an explicitly defined sequence, we can use n to find any term, no matter what n is, directly.